I've got homework 3, just handed out homework 4 to you. It's due on Monday the 11th. It's only got 2 problems. How hard could it be? No, it's not hard. It's beautiful. We're going to spend just a few minutes concluding our investigation of pipes in parallel, and then talk about what's called the Hardy-Cross method. And that's pretty interesting stuff. So any questions on the schedule before we move forward? This is what we were finishing with last time, where we went through the process of, in the example we actually worked, ignoring some of the wider issues of the network. And that's actually a point that I want to emphasize to you, is that you don't have to solve everything in this kind of problem in order to find the relative flow rate through each pipe. There is a whole procedure of finding the pressure at each junction and knowing the head at each junction, but really, because the governing relationship is just that the head loss through each of the pipe routes is the same, you can end up finding the flow rate through each of the pipes without knowing what the pressure is at junction B or junction C. Remember that the main relationship that governs is that the head loss due to pipe friction through pipe 2 is equal to the head loss due to pipe friction through pipe 3. And then it was that substitution we used to find the velocity through each pipe. Because remember, head loss due to pipe friction, according to the Darcy-Weisbach equation, FLV squared divided by D2G. And so we did all of that through pipe 2, and then we related it to everything through pipe 3. Once we know the flow rate through each of the pipes, then applying the modified version of the energy equation to find the head at some location is relatively straightforward. Now this equation, we didn't get to see the effect of this absolute value of Q. Does anybody remember why it's an absolute value of Q? Exactly. It's because sometimes if the flow direction is going a certain way, we'll call it negative flow. And when it's a negative, we want to still see the negativeness of the negativosity of the flow direction. So we only find the absolute value of one of them. And that's why we put that term in front of the pump head too, is because if it's going the opposite direction from 1 towards 2, if it's actually going from 2 towards 1, then that would be a negative flow, and then we shouldn't be adding the pump head any longer. We should be subtracting it according to that convention. So we didn't get to see that in the example that we worked last time. That example was really more about this idea, the idea of the head losses being equal. But we will get a chance to use that. And in fact, you need to on this homework 4 that I've just handed out. You've got this, we've got this pipe network, and you're going to have to assume a flow direction, and certain flow directions are going to be either positive or negative, and we'll get into that. But that's when you're actually going to be applying that modified version of the energy equation. So any questions that came up as you thought about and pondered this example from last time? All right. This is one of the 2 problems on that next homework assignment, and it throws you for a loop, or throws you for a junction maybe, because last time in the example what we looked at is there were only 2 flow paths between the entry junction and the exit junction. So it was either going through the top pipe or the bottom pipe. But now there's actually a middle route as well. And I give you a hint to how you can solve this problem by asking a question there on the slide. So how would, in this case, what do you think the head loss situation is through those 3 different pipes? Equal in all 3, exactly. So it looks like the middle route, pipe 1, is a small diameter pipe, 2 is medium, and 3 is large. And so maybe just based on nothing else, we'd imagine all the relative flow through pipe 3 is maybe the greatest and so on, but the head losses through each of those pipes is going to be equal, because what we know is it comes into an equilibrium so that there's no best flow path for water to go through. It's going to look at all 3 of those routes and say, it doesn't matter which one I go through. I'm either going to go through the middle route, and it's like a lot of energy loss because it's a tight squeeze, but less of the water will go through there. And so just naturally, more of the water will go through the big pipe, and so the velocity will be higher, and it'll all just come into equilibrium so that what's equal through all those 3 different routes is how much energy it takes to get through it. So that the beginning energy state as the junction appears, and when the pipes come back together at the exit junction, they all have experienced the same losses and end up with the same amount of head coming out of it. So that's the hint, is that, in other words, if we extrapolated that to the Darcy-Weisbach equation, what we could say is that F1 L1 V1 squared divided by D1 2G will equal all of that for 2. And we'll equal all that for 3. So it's going to be a system of equations. You're going to have to know the flow rate through one of the pipes in terms of the other. Remember that the continuity relationship will be that the total flow rate is Q1 plus Q2 plus Q3. And so you're going to use this to express the velocity through pipe 1 in terms of the velocity in pipe 3. And you'll be able to do 2 in terms of 3. And so we could say A1 V1, A2 V2, A3 V3. And then what you're going to do is you're going to say V1 as a function of V3. And the same thing here, V2 as a function of V3. So that then now only unknown is the velocity through one of the pipes. You've got a relationship that explains how the other velocities relate. How does velocity 1 relate to velocity 3? How does velocity 2 relate to velocity 1? It doesn't have to be all in terms of velocity 3. It could be any of them. I just picked that at random. You could solve the whole problem in terms of the flow through pipe 1, and it would still work out, and you'd still get the same answer in the end. But it's a system of equations. I feel like I kind of gave away the farm on that one. I want to balance it out. I won't give any hints to the next section, to the 1 o'clock guys. Then between too much and none, it'll be just the right amount of hints. Right? Yes. Yeah. Okay, well, let's talk about a different method, because this is awfully simple. It doesn't feel simple, maybe, because you're having to guess the F value and then check the F value, you know. Fingers crossed that it's fully turbulent flow, and then it's not fully turbulent flow, so you have to do the whole thing over again with an updated F value. That's simple. What's less simple is when you've got water going into a pipe network. And the reason why this is less simple is because you don't know how much water is going to be going through any one of those different pipes. And water can take lots of different paths to go out. And in fact, there may be different places that water comes in and goes out of a pipe network. And so this Hardy-Cross method, as it's called, or the loop method, is used in systems that are more than just an entry node and an exit node. It's where there can be multiple nodes in a system and lots of different flow routes to go through the network. This loop method is actually what WaterGems uses to solve problems. It is used to find the flow rate through lots of complex pipelines, and it's going to be applying the same principle that I was just mentioning in this situation, that if we're entering with a certain amount of pressure, and there's going to be some certain amount of pressure at the exit, some water will go this way, some of the water will go this way, maybe some of the water would go that way to finally get to the exit. You know, a portion may be going through lots of different flow paths, but ultimately, regardless of the flow path, it loses the same amount of energy. And that's the principle that is built into the Hardy-Cross method, is that we're checking all of this different flow routes that water can go to get from point A to point B, and we're trying to balance it out so that water has the same amount of energy loss regardless of which path it takes between the 2 points. And so we're having to sort of manually juggle all of those different routes. Like maybe we'll make some initial guess of how much water is going through a certain pipe, and then we'll check it. We'll see, well, did we guess too much water going through that route? And if so, then we'll move a little bit of water through a different pipe and then check the energy balance again. And the nice thing about this is that when I said we'll move a little bit of water from one pipe to another, we don't have to manually interact and do that. There is an equation that will, for us, it'll make the correction. It automatically makes the correction so that once we set up the spreadsheet, we can just copy and paste multiple times, and it'll just sort of automatically converge on the right solution. And so that's what we really like. We like these iterative solution processes that can think for themselves, so to speak, that don't require any interaction from us, that we just set it up and start copying and pasting, running iteration after iteration, and it naturally converges on the right answer. So that's what the Hardy-Cross method is. It requires you to guess initially how much water you think is going through each of the possible flow paths, and then through a series of iterations balance that to make sure that none of those different flow paths has a different amount of energy loss than the other. Because if there was, that would be crazy. The universe would explode. There's different ways to do that. You can either set it up by hand and do these calculations over and over and over, and that's what we're going to do today. Is we're going to do a hand calculation of the Hardy-Cross method, and then it's by doing it in this really time-consuming method that ultimately you will have earned the right to solve it by a spreadsheet, and you'll appreciate how easy the iterations are, in spite of the fact that it takes some time to set it up. And then the Hardy-Cross method is what's built into water gems, and so it's really powerful, but if you don't understand the underlying math and you don't understand the limitations, then it's easy to perpetuate big mistakes when you're using a computer. So hopefully through the process of trying it out by hand and setting it up on the spreadsheet, then you'll be in a better position to use water gems responsibly. The first place that we're going to start is by calculating resistance to flow through a certain pipe. The Darcy-Weisbach equation, H sub F, is FLV squared divided by D2G. We're going to transfigure that a little bit so that we can use it in the Hardy-Cross method, and we're going to group together some things that aren't going to change. You know, regardless of what the flow rate is, well, maybe I should say it a little bit differently. We're going to group all of these terms together and throw in A squared and change this to Q squared. So all of that is going to be R. So you can see here in this formula, head loss is R times Q to the n power. You can do the Hardy-Cross method in using the Hazen-Williams method of energy loss. Remember, Hazen-Williams is easier because the C value doesn't change as a function of flow rate. And if you're using Hazen-Williams, N is 1.85 instead of Darcy-Weisbach. But we're not going to use Hazen-Williams. We're going to go all the way, use the full-fledged Darcy-Weisbach method in spite of the fact that calculating in spite of the fact that calculating F is a little bit challenging. We're going to go for it all the way. So the first thing you do when you're trying to solve this pipe method is you say, all right, well, I've got a certain pipe here. What's the R value for it? You know, for this pipe length that is given to me for the diameter of the pipe, using my first guess of what the F value might be, the cross-sectional area, all those parameters that go into R, what's the resistance through that pipe? And the higher the R value, the more resistance there is to flow through the pipe, and that gives you a relative idea of what the flow rates might be. If there's a certain flow path that has a really big R, that means either that there's high friction factor, long length, or small diameter. So less water is going to go through a route that has a high R than a route that has a small R. And so that can help you making that initial guess of what the flow rates might be, your initial guess. After that, once you start putting it into the iterative method, the method will take care of any bad initial guess that you make. So don't be too paralyzed in identifying that first guess flow rate. It'll converge a little faster if you make a good guess, but Excel's doing the heavy lifting anyway, so it doesn't matter too much. So we calculate the R value for every pipe in the system, and what N is depends on if we're using Darcy-Weisbach versus Hayes and Williams. Also, in this approach, you can see that we're neglecting local losses. But we're only including frictional losses. And those can be added in if we want to account for them. But just so that we focus only on the approach of the method, for now we'll just look at the friction loss only. So here's how we calculate R. This is the definition of R. So from iteration to iteration, R may change. Like during our first iteration, when we guess our F value based on the fully turbulent assumption, we'll have some R. But then in the second iteration, we're going to update our guess of F, and we'll have like a better guess of F. We'll use the Jane equation in our second batch of iterations, and so R will be a little bit different. It's not going to be hugely different because, if we make the fully turbulent assumption and we get an F value of 0.02, and then the Jane equation tells us, no, it was really 0.023. I mean, our R value will change by maybe 10 or 15% from the first to the second iteration. Then R will stabilize after that. So here's an example of how to calculate the R value. 400 liters per second flowing through a 750 millimeter diameter concrete pipe that's 85 meters long. So will you please calculate the R value for that conduit? You can use the Jane equation. You can use the Moody diagram. Whatever you'd like to do to handle F.
Based on rounding, we have like 400s of additional.
Yeah. Well, the beauty being that what's a good margin of error? You're going to be putting this into Excel, and it'll keep track of all the digits, and your F value will be calculated based on the Jane equation. So it won't be that you looked up a bad value off the Moody diagram. So I'd say, if you were actually working this by hand, the flow rate that you get is going to be a function of the R value directly. So, this level of precision, I wouldn't worry about it being 7.103 necessarily versus 0.71. But in Excel, that consideration becomes a moot point. Okay, so that's resistance to flow. Now, here's the procedure itself. I'm going to give you a handout in a minute, but let's consider this pipe network. Okay, in this pipe network, 100 units of flow are entering in the lower left, and exiting through these other junctions, 20 units of flow out here, 50, 30 units of flow. And they've calculated the resistance values based on all this known information. And so the process that we have to go through to find out how much water is going through each of the pipes is shown here, and we'll talk through it in just a minute. So what are the givens and what are the unknowns? The flow rate in and out is a given because what really governs things is how much water they're trying to get out at this junction. Like, how do they make it true that 20 is coming out here? Well, they've got a valve and they're opening it to whatever setting they want that's going to give them the flow rate they desire. So by definition, they're getting the main given is the flow rates out. The flow rate into the system is dependent on the flow rates out. It's not like we're forcing in 100 and it's spurting out of the network according to this pattern. That's not it at all. It's actually that at these junctions, someone is drawing that specified amount of water, and because of the continuity relationship, therefore 100 has to go in to satisfy the demands. And so we first look at this process and ask, how many loops are there? I bet you can guess. There's 2 loops. So let's go through here. Look in this example. Okay, step 1, 2 loops. Okay, step 2, what is N? Since we're going to use the Darcy-Weisbach equation for energy losses, N is 2. N is 2. All right, step 3, define the direction. What I mean by that is we have to define some sort of convention for what is positive flow and what is negative flow. And I propose that we do the following, that we say clockwise is positive. And for consistency's sake, let's always have clockwise be positive. It'll be simpler for us all if we just stick with that. There's nothing magical about it. What I'm going to say is clockwise is positive. What do they call it if it goes the other direction? Right. You know in English what they call it? Anti-clockwise. See? This is engineering and culture. So label the pipes and the loops. I'm going to give these labels, let's see, what would make sense? If I called this junction 1, and I'll call this junction 2, 3, and 4. And the way that we're going to refer to pipes is we'll call a pipe like pipe 1, 2. And that doesn't necessarily mean that water is going from 1 towards 2. And so I could just as easily call that pipe 2, 1. It's just referring to a pipe by its 2 terminus points. Okay, so step 4, label pipes and loops. Okay, label the loops. I'm going to call this loop 1 and loop 2. Find R values for pipes. They did that. Assign guess value. I'm jumping ahead. Step 5 is the most fun, actually. Okay, we've got 100 going in, 30 going out here, 50 out here, and 20 going out here. Okay, there are rules and there are suggestions. The rule is continuity cannot be violated at a junction. Since I've got 50 coming into this junction, I can't have 200 coming out. I've got 100 coming in, there's got to be 100 going out. So at this junction, there's 20 going out. Somehow, through these pipes that are feeding that junction, all of them combined, it has to be 20 going out. That's the balance. So that's the rule. The suggestion is that if you've got a big R value, maybe less flow is going to go through there. So let me show you what I mean. Pipe 1-4 has an R of 6. Pipe 4-3 has an R of 5. So I'm guessing that probably more water is going to go through 5 than through 6. And so what I've got to do is I've got 100 here, and I've got to split it between those two. I'm going to just say 55 that way and 45 that way. Ultimately, the spreadsheet's going to make everything work, and so it doesn't matter. If I would have just said 50-50, that would have been fine too.
Yeah, it's conceivable that pipe 4-3 would get 6/11ths of the flow coming in. That's basically what you do. You look at it that way.
Yeah, but that's not what it will be in the end. There are other factors. I don't think that the relationship is linear and proportional quite like that. But that's how I set it up to begin with, is assuming that it is. And so you could use those R values as a relative ratio. And so what I'd like you to do is, let me erase my guess. In your own notes there, figure out the balance. Come up with a guess. In fact, let me give you this handout here. You can draw on this handout what your guess of the flow rates are. So indicate with an arrow the direction you assume the water is going, and also right next to it the flow rate. Okay, so right on the page there, use a pencil so you can erase it if and when you make a mistake. How much flow is going where? Get it to balance at all of the junctions. Double check with the person sitting next to you. Make sure that theirs makes sense. Try and catch their mistake. Have them catch yours. All right, I've got one on here that balances. Yours probably is a little bit different from mine. As long as it balances, that's fine. And maybe it's easier just to ignore the R values if you're having a hard time doing the flow balance. I could have just as easily said, at this decision point, what if I said 1 and so I'm getting rid of 15, 14.
That'd be 24. So 14, would that be 24?
I don't think so. Is it?
55 coming in.
55, 25. Oh, yeah, you're right. Thank you. Do it without a calculator. 24, 69, 40 gallons, 40. Yeah. So you could even make crazy assumptions and still do a flow balance. And ultimately, even with the worst assumptions, it will converge because Hardy Cross was such a good guy. This is actually a procedure that he figured out for structural analysis. And somehow there was an analog between structural analysis and water flow through pipes. He was an an engineer that worked at the University of Illinois Champaign-Urbana. And this is like an indeterminate analysis procedure that has applications in multiple areas of engineering. Okay, so we've come up with our initial flow balance, and so we've got our guess flow rates, we've got R values. Now there's this process of finding R, Q, absolute value of Q, and NRQ for every pipe in the loop and each loop. And so I've just given you a paper here. So in iteration 1, let me put on the board here and you can follow along. Use your own numbers, but okay, first of all, we've got iteration 1. Okay, loop, we're going to first look at loop 1. And the pipe I'm going to look at in loop 1, now I decided that it was, well, it's here on the page. Okay, so loop 1, I'm going to look at pipe 1-4 to begin with. 1-4, 1-3. Okay. What's the N value for each of those? We're using N value is 2 for all of them since it's Darcy-Weisbach equation. The R value for those pipes is 6, 3, and 5. That's off of the figure. The Q, I'm going to change away from my ridiculous guesses and get some reasonable guesses in here that I'm going to base my calculations on. I'm going to base it on 50, 50, 15, and then over here that would make it 65, so 35. It would have to be 15 here. So does that work? 50? No, it doesn't work, does it? 50, 50, 15, 2, 3, like 2, 3. No, I'm not going to do 2 3s. This is going to be 35. 50, 65.
Wouldn't that have to be 5? So you got 15 going up. Unless you got 15 up there.
50, 15. I'm going to go with 50 here, 35 there, and 15 actually this way. All right, now I got it. Okay, so when I put in the flow rates, 1-4 is 50 because it's in the direction that I've assumed is positive. Remember that this clockwise means it's a positive flow rate. So pipe 1-4, the flow is going clockwise in the perspective of loop 1. This 50, though, it's going the opposite direction of clockwise. See how it's from the left towards the right? Well, loop 1 is actually going the other direction. And so that flow rate, when I write it down on the board, is going to be negative 50. So my flow rate for pipe 1-4 is 50. For 1-3 is 15. And then pipe 3-4 is negative 50. Any question about the sign convention with the negative sign there? Why that is? So you can be following along with your own numbers if you like, or you can write down mine. Either one's fine. Okay, now we're going to calculate R times Q times the absolute value of Q. If I multiply R times Q and the absolute value of Q, I get 15,000. If I do it, same thing here, 675. Do the same thing here, negative 12,500. And I want to add all that up. The sum of those three things is 3175. In the next column, I'm going to calculate n times r times the absolute value of q. So I'm going to now use this n column. 690, 100, and 1190. Add, that's it, everything added up. Now, the next column is I'm going to be calculating some delta Q. Delta Q. And what that is it's delta Q is the negative of this divided by that. So it's, as is shown, I think, on the other side of the handout I've just given you. The formula for delta Q, no, it's not there. All right, well, let me find that real quick, and I'll put the formula for delta Q. I don't have it on here. I'll just write it on the board. Do it the old-fashioned way. It is delta Q is the negative of the sum R Q, absolute value of Q, divided by the sum of N R, absolute value of Q. So what I'm going to have is, in this case, negative 3175 divided by 1190. And so the delta Q is negative 2.668 for all of them. That's an energy balance technique. And my corrected Q is combining the initial flow rate and the delta Q. So 50 minus 2.668, my first correction is I'm going to adjust the flow rate that's going through that pipe and say, well, my improved guess is that it's 12.332 instead of my initial guess of 15, negative 52.668. We're going to continue this example when we get together on Friday, but that gives you a sense for where we're headed. We're going to be looking at each pipe, its flow rate, its flow direction, and then balancing in the loop. You can continue on with the example if you're inclined, see if you can figure it out. But there is one key step, and that is that if there is a pipe with that is in a common loop, this pipe right here that's in both of them, the flow direction when I'm in loop 1, that's a positive flow direction. But when I'm in loop 2, it's a negative flow direction because, see, I'm going against what loop 2 sees as the clockwise direction. So we'll get to that next time.